Okay, hello everyone. So in this video, we are going to cover part of chapter 13, solutions. So this chapter talks about what is a solution, how do we talk about them, how do we talk about their strength, and how do different things kind of dissolve in liquids, and what happens when something dissolves in a liquid, and then what happens with that solution. Does that solution have different properties? So those are some of the answers that are some of the questions we're going to answer throughout this lecture and the next. So in this video specifically, we're going to kind of give a broad overview of some definitions about solutions, and from there we're going to talk about strength of solution, aka concentration. So let's get started. Now, is alcohol a solution? Well, technically I say it is, because in chemistry, yes, it's a solution. Now, to solve all your life problems, nah, it doesn't work quite like that. Probably not a solution there. So please, don't think I'm endorsing alcohol as a solution, but is it technically a solution? Yes. Yes, it is what we consider to be a solution in chemistry. So in this chapter, we're going to learn about what makes a solution a solution. And along the way, we're going to learn about other systems like pop and rock candy and salt on the roads and deadly burping lakes. So all of these different solutions, these are all examples of solutions that I've given you, rely on different properties of solution to cause their behavior. So eventually we'll get to talking about all of those fun topics, but first we got to get to some boring definitions. So let's get through that. So we got to do some quick reminders here. We did talk a little bit about solutions in Chapter 3 in Unit 1, but that was a while ago, so some of these terms may be familiar, so I just want to jog your memory about them. So for Chapter 13, what we're going to consider to be a solution is a homogeneous mixture of two or more substances. So remember, homogeneous means a consistent mixture throughout, so it doesn't matter whether I grab from the top of the sample or the bottom of the sample, for example, I'm going to get the same exact thing. Whereas, remember, heterogeneous mixtures are opposite, where you might have something different in different places in your mixture. So we're talking about very specifically here a homogeneous mixture of two or more substances. So that is what we're going to consider a solution to be. Now, if you check it out down here at the bottom of your screen, you can see that there may be different kinds of solutions made of different kind of phases or states of matter, okay? So if we have a solution in the gaseous phase or in the gaseous state, that might be two different kinds of gases mixed together. So that might be something like air, where it's mainly oxygen and nitrogen. Remember, we talked a little bit about there being some argon, some CO2. I mean, there's also carbon monoxide in the atmosphere as well, of course we know, but carbon dioxide has a bigger proportion. So all of those gases mixed together make the solution of air that we breathe in and breathe back out. So technically, you're breathing in a solution every time you breathe in. We also might have solutions in the liquid state. So this might be a gas dissolved in a solution like my Mountain Dew. Or that might be two liquids dissolved in each other, like, looks like it says here, vodka, ethanol, and water. So the alcohol we drink is ethanol. So ethanol and water would be an example of a liquid dissolved in a liquid to make vodka. Well, to dilute the vodka enough so it's relatively drinkable. And then we might also have something like a solid dissolved in a liquid, which we're quite familiar with when we've been talking about so much about dissolving ionic compounds. So that might be salt in water, like seawater, for example. So those are a few different kinds of solutions there. We may also have a solid solution. We're not going to spend very much time on solid solutions, but that might be like brass, which is actually made up of two different elements. You know, brass isn't on our periodic table, so it's made up of two different elements, copper and zinc, or like other metal alloys like steel, for example. So any metal alloy is going to be a solution of solid, for example. So solutions aren't necessarily always in the liquid state. They may be in any state. So as long as it fits that bill of a homogeneous mixture of two or more substances, regardless of the state, that is still going to be a solution. So a couple more terms to get out of the way over here are that the solvent is the thing that does the salt dissolving. So if something is being dissolved, it's being dissolved into a solvent. So this is going to be relatively usually the substance that is in the majority. So it's going to be whatever you have more of that is likely going to be doing the dissolving, that we can make that assumption of in this class. So we'll always consider the solvent to be the majority substance. You may also have the solute, or well, you do have the solute in a solution. There's no might about it. You absolutely have a solute in solution. And this is what we call the minority substance. So this is the thing that we have less of, so therefore it's the thing that gets dissolved, right? So usually we might have like a saltwater solution, for example, we talked about. So that might be NaCl being dissolved into water. So for example, NaCl is our solute, and H2O, water, is our solvent. So solvent is the thing that is doing the dissolving, and solute does get dissolved. So that's kind of the idea there. For the rest of this chapter and for the rest of the time in our class, I am going to be using the words solute and solvent and solution. So you should become very familiar with those terms and make sure you keep solute and solvent straight. So the last kind of quick definition that we need to get out of our way is concentration. So we've talked about this a little bit. You may have heard me mention it before, and you may have heard concentration in terms of solutions before, but I want to make sure right now that you know that what I mean is kind of the strength of the solution. So how much solute did you actually put into your solvent? Because, you know, if I'm cooking my pasta water and I add 3 teeny tiny grains of salt, oh, I could salt bay it. I could add 3 grains of salt into my big old pasta pot of water, and I'm probably not going to taste it. But if I add 3 tablespoons of salt into my big old pot of pasta water, the same amount of water, I'm probably going to taste the salt in that case because I've made a stronger solution. I have a higher concentration. So stronger solutions have higher concentrations, weaker solutions have lower concentrations. So concentration, we have different ways to measure it, but it is some sort of measure of how much solute is contained in the solution or how much solute there is compared to the solvent, okay? So it's some measure of the strength of solution. For example, like if I'm talking about strength of solution, I'm talking about concentration. One thing you might be familiar with, since we're on this kick of alcohol as a solution, is that we buy alcohol by proof. But what does this really mean? So it's 2 times that ratio of alcohol, aka ethanol, to the total amount of solution present. So this is basically saying that it's like the percentage of alcohol times 2. So the other parts of the solution are definitely going to be water, and then other things of flavoring. So that might be things like sugar or like the char of the barrel getting mixed in. That's going to take molecules into our solution as well. Any kind of flavoring you're putting into an alcohol solution that you're going to drink is a is a part of the mixture here in alcohol. So what I'm trying to say is that like the highest proof of alcohol or the strongest solution of alcohol that you can buy at the store is going to be Everclear, which is 190 proof, or approximately 80% of alcohol in solution. So to go any higher than this, you actually need special permits, and you need to purchase it for a reason. For example, be a chemist. We often have contact with 100% pure alcohol because we may use it in our chemical reactions or experiments. So you can't actually buy super pure alcohol at the store. It's always good to have some form of dilution with it. It's going to have something else mixed in. So kind of a cool fact. So proof is how we talk about strength of an alcohol that you're purchasing at the store. how do we talk about the same thing in chemistry? Like, how do I talk about that strength of solution or concentration in chemistry? Since we're familiar with proof, that's what's going on here, but how do we talk about the same thing in chemistry? So we use something called the molarity. So the molarity is a way to express the concentration of the solution by using the amount of solute in moles compared to the total amount of solution in liters. We're going to start out from the start, and I'm going to say everything we are doing in this chapter is in moles and liters. If you see any other unit, convert. Now, do it. We are always in moles and liters in this chapter. Molarity is written here as an equation, and it is always moles of solute divided by liters of solution, okay? So what I want to point out here is it's liters of total solution, okay? Moles of solute divided by liters of total solution. So, for example, if you want to make a solution of salt in water and you want to make sure you're exactly making 1.00 molarity, we'd say 1.00 molar. That's the word we use for the unit of molarity is molar. So if we want to prepare a 1.00 molar solution, we're going to want to put 1 mole in 1 liter, for example. So in the picture here, you see that you are adding 1 mole of NaCl, and then you add the water to dilute it. Because the problem here is we're not talking about moles of solute compared to liters of solvent. So I'm not going to end up actually adding a full liter of water because some of these salt molecules, all of them, not some of them, all of these salt molecules in solution, what's going on is they take up space as well, right? They have a volume. So when we add the water in, if we added a full liter of water, what would happen is that we end up with a volume that is greater than a liter, so we don't have exactly a 1 molar solution. So anytime you're in the lab and you want to make a solution of a certain concentration, you always add the amount of solid first, or add the amount of solute first, and then you would fill with the line, or fill in the volumetric glassware up to the line that you wish with that amount of liquid. So that's kind of generally how that's going to work. So I want, again, to make it clear that it's moles of solute divided by liters of solution. So it's that whole total amount of solution, not just the amount of solvent, okay? Anytime you see molarity, you can always assume the underlying units are moles and liters. So you could say this is, if you saw this M somewhere, M is the abbreviation for molarity, a capital M. We always use capital M. This is why we do not use capital M when we're talking about meters. And this is why we don't use lowercase m when we're talking about molarity. Because unfortunately, we've kind of got a lot of different letters meaning a lot of the same stuff. So we try to use the capital and the lowercase to distinguish them. Tangent over. Anyways, that capital M, if you see that capital M, can always be written as moles divided by liters. So if you ever want to break down that unit and you want to figure out what's going on, you could always translate your capital M to moles divided by liters, for example, which you'll see when we get to working through some problems. And what I want to remind you again of is that molarity takes into account how much solute there is for a total amount of solution. So you don't want just information about the amount of solvent, you need information about the amount of total solution. So let's go ahead and work through some examples here on how to do these calculations. All right, so let's go ahead and do the first example on how to calculate molarity of a solution. We want to know what is the molarity of a solution made up of 0.567 moles of ethanol and 2.6 liters of solution. So let's go ahead and calculate this. Well, we know that molarity is moles of solute divided by liters of solution. So that tells me that here I have 0.567 moles of ethanol being that is in an entirety amount of solution of 2.6 liters. So if I go ahead, I math this out, this makes sense to me. I've got moles per liters. Molarity is moles over liters. I am in the right place. If I go ahead and type this into my calculator, I get 0.21807692331 molar. And from there, it looks like in our problem that we have 3 sig figs from 0.567 moles and 2 sig figs from 2.6 liters. So that means my answer should be in 2 sig figs. So I'm going to record my answer as 0.22 molar. So if we ever see that M as a unit, we call it molar. And it's always a capital M if we want it to mean molar. Okay, so that is your first example there. Let's go ahead and do the second example in this section. So we want to know what is the molarity of a solution made of 54.36 grams of Ki in a total of 845 milliliters of solution. So just as before when we were talking about R, the universal gas constant, we always had to make sure that we converted our units to match the units of R that I gave you. Here, we always have to be sure that we convert our units to match the units of molarity, which are moles per liters. Here, we're given grams and milliliters. So, to figure out how many moles of Ki we have, we are going to need to figure out how to convert from grams to moles. Well, we've done this once before. You use the formula mass. So you go to the periodic table, you figure out how much how much mass Ki has in the periodic table, and then you add the mass for potassium to the mass for iodine, and then you have the grams per mole. So when we're looking at the periodic table, the number that we see for mass is going to represent grams per mole again for us. So that being said, I have 54.36 grams. And if we add up the mass of potassium, that is 39.1 grams per mole, and we add that to the mass of iodine, which is 126.90 grams per mole, what we end up with is a conversion factor that says the formula mass of potassium iodine is 166 grams for every 1 mole. So when I'm converting, I always have to make sure that I want my units on top to cancel with my units on bottom. So if my conversion factor is 166 grams for every 1 mole, that means here we have 166 grams on bottom for every 1 mole on top. Because I want moles, so I want my grams to cancel, which checks out. I have grams on top, grams on bottom, cancels out. I'm left with moles. And if I do that math, I end up with 0.327469879 moles. What you'll see here is that I tend to leave my answers in all the numbers until I get to the final point of rounding. We haven't exactly talked about this in this class, and I think it's a little bit beyond us to have to determine what should be rounded and what should not be rounded, because if we were in lab and we were practicing these skills all the time face to face, we may have already experienced a lot of this. However, for our purposes this semester, I don't care if you round that number or you choose not to round that number. I just have to see what's going on. So that being said, I also need to convert milliliters to liters. So I'm going to go ahead and do that as well. So we have 845 milliliters. There are 1,000 milliliters for every 1 liter. So milliliters on bottom, milliliters on top so that they cancel out. Milliliters on top, milliliters on bottom. Those guys cancel out. So I'm left with liters, and that's going to be 0.845 liters. So we now have the values we need to be able to calculate molarity, because now we are in moles, check, liters, check. That's what I want. I can go ahead and calculate. So molarity is moles of solute divided by liters of solution. You may see me use this quick abbreviation for solution, SOLN. That just means solution. So moles of solute divided by liters of solution. So that means I have 0.32746987995 moles over my 8.4. Oh, I didn't write the number 8. There we go. 8.45 liters. So I am left with, actually I'm going to go ahead and write my number down here just so I have a little bit more space. So that's going to be left with 0.387538319 molar. That's actually what I see in my calculator. However, remember, we gotta triple check sig figs. So 4 sig figs from the mass and 3 from the volume. So I'm going to go ahead and put this in 3 sig figs. So I got 0.388 molar as my answer. So that is how we solve some examples for how molarity works. So stop my screen recording here. So that is how you calculate information for molarity. So I've left you 2 other practice problems to work through that I've worked out in the slides. So if you're interested in checking out those, go ahead and check those out, work them out, and then let me know if you have any questions. I also want to let you know that molarity isn't just this concentration that we arbitrarily use to measure strength, right? We actually can use molarity as a conversion factor to determine the amount of moles of solute or the total amount of solution, for example. So this is sort of like how we used density as a conversion factor before. We were talking about like grams per volume. Here we're talking about moles for an amount of solution. It's kind of the same thing. So if I know the molarity and I know the amount of solution, for example, I can figure out how many moles were in there. That's kind of where we're headed. So because molarity tells us about the amount of solute in total amount of solution, you can use the molarity to quote-unquote go backwards and to determine the amount of solute or the amount of total solution. So, okay, so we're going to go ahead and work through the first example that you see in the molarity and calculation section. So this problem says, how many moles of NaCl should you dilute to 0.500 liters with water to make a 3.4 molar solution? All right. So in this case, we are given that the molarity is 3.4 molar. We're given a volume of 0.500 liters. And what we're looking for is a number of moles. So in this case, what we can do is if we just think about how we set up our information for molarity, molarity is moles of solute. I'm just going to write moles solute divided by liters of solution. So here I have that we actually know the molarity. So the molarity is 3.4 molar. But remember, anytime we see that capital M, we can always write it as moles divided by liters. And I don't know my moles of solute. That's what I'm looking for. So I'm going to go ahead and put an X there. You can use any letter, any variable, anything you want to hold that place, as long as you remember that X means moles of solute. I'm going to go ahead and put my X there. And then I need the amount of liters of solution in the denominator, which is going to be 0.500 liters. So What I can do from here is go ahead and solve for x. So I have to clear out that denominator of half a liter. So I'm going to go ahead and multiply both sides by 0.500 liters. And then what I'm left with is that x equals 3.4 moles per liter divided by, or I'm sorry, what am I thinking? What we actually have is 3.4 moles per liter times that 0.500 liters. So if I'm looking at this, I can start to kind of break down what's going on and determine if I'm in the right place. So if I check out my units as I have it written here, x is by itself, so x has been solved for. Let's make sure we have the right unit. So here I have liters on top, here I have liters on bottom. I'm left with moles. That's what I'm solving for. It says number of moles over here. I'd say we're good to go. So my x is in the correct unit, so it's going to represent the number of moles. So what that means is I have 3.4 moles. 3.4 moles divided by, or multiplied by that 0.5. So I end up with 1.7 moles as my final answer. So if I type that in my calculator, I type 0.5 times 3.4. What I get back out is 1.7. If I go back to my problem, I have 2 sig figs, 3 sig figs. So I meant to have 2 sig figs. So I'm just going to write down, in this case, what I see in my calculator. And I'm just going to kind of triple check here. So I have 1.7 moles. 1.7 is in the correct amount of sig figs. Moles is what I was solving for. So I don't have any red flags or alarm bells ringing on this one. So I'd say we are doing good. So let's go ahead and do the second example in this section as well. So this example says, if you want to have 89.34 grams of CuSO4 in solution, how many liters of a 2 molar solution do you need? So here we're given a mass and we're given a molarity and we want to find liters. So we are given that we have 89.35 grams of CuSO4. And we also know that we have a 2.00 molar solution. And what it's saying that we need here is we're looking for how many liters. So how many liters means we're looking for a number of liters. So I hope something's ringing a red flag or ringing a bell for you that's throwing up a red flag. I don't know what you want to say, but I hope you notice that there's something different about my problem here. And then in this case, I have grams, but remember, I always have to have moles. So I'm going to go ahead, go to the periodic table, figure out that formula mass, and then use that to convert. So if I have 89.35 grams of CuSO4, what I'm going to do is add up the mass for copper, for sulfur, and for 4 oxygens. If I go ahead and do that calculation, what I find out is that I have 159.61 grams for every 1 mole. Well, remember, we want to make sure grams cancel out and we want to be left in moles. So I'm going to put grams on the bottom so that 159.61 grams is going to go on the bottom, and on the top we just have 1 mole. Remember, our periodic table shows us the information in grams per mole, so I have to make sure I'm using my conversion factor correctly by making sure my units cancel. So grams on top, grams on bottom, that cancels out. I'm left with moles, which is what I was interested in finding at this step. If I go ahead and I multiply this out, I have 0.5598 0.020174 moles. So now I have all of the information that I need to solve this problem. So I have moles, check, molarity, check, and I'm looking for liters. I am on the right track. So that being said, let's go ahead and plug into our equation and solve. So molarity is always moles solute divided by liters of solution. So molarity in this case was given as 2.00 molar. We're given this time information that led us to the moles of solute, so that's going to be 0.55980200174 moles. And we're looking for liters of solution, so I'm going to go ahead and put an X down there. So next things next, I got to get X by itself. Again, there may be multiple ways to solve this problem. What I am going to show you is how I would solve this problem. So I would multiply both sides by X so that what I'm left with is 2.00 molar times X equals that 0.55980200174 molar. From here, I'm going to go ahead and divide both sides by my 2.00 molar, in which I should have done this before, but I haven't done it until now, which is okay, it doesn't matter. Remember, that capital M is the same thing as moles divided by liter. So I'm going to call that moles divided by liter. 2.00 mole divided by liter. So these two are the same thing. They cancel out. I'll put that in red to make sure you can see it nice and bright. So I'm left with X on the left-hand side, and I got some tricky work to do on my right-hand side. So X in this case equals 0.55980200174 moles. Again, divided by 2.00 moles for every liter. So if I'm looking at my units, really here I have moles on top and I have moles on the bottom in the top of my fraction. So again, if I've got a little fraction underneath a big fraction, I can flip it, but whatever is on the bottom of the little fraction goes up to the numerator, and then whatever is on the top would be in the denominator of the big fraction. So in this case, I have that X equals this. It's going to put liters on top in the end. So when I go ahead, I do that division. The answer that I get is 0.27990100087 liters. And if I put that in the correct number of sig figs, in this problem, the correct number of sig figs is 3. So if I want to round that, I would write that as 0.280 liters. So that's my final answer, 0.280 liters. Okay, so that is how you do that's how you tend to use molarity in these problems. So go ahead, make sure you check out those practice problems you see on your screen as well. Please make sure you ask me if you... Okay, so we have one last little topic to cover here in part 1. So we've kind of talked about how we determine the concentration and how we deal with those things. However, sometimes solutions are just a little bit too strong, right? Not everyone, no one, should be drinking pure Everclear. So how do we talk about the strength of mixed drinks? So how do we figure out actually what the concentration of alcohol is in our total amount of solution if we make a mixed drink? So if we add some other liquid to dilute it, right? So we're just thinking here about dilution, which is the process of lowering the concentration of a solution by adding more of a solvent. So in this class, we're always going to be talking about adding the same solvent that's always in solution, so we don't have to worry about lots of complicated, messy things, whereas, you know, your alcohol is originally dissolved in water and we're adding maybe pop or something. I mean, unless you drink vodka waters. I don't know your taste. But I'm totally kidding about the alcohol stuff, guys. I'm not endorsing any sort of drinking, please. So, but you know what I mean? Different people have different tastes. So how can we figure out that concentration of your original alcohol solution if we add something to dilute it? So again, dilution is that process of lowering the concentration of a solution by adding more solvent. Oftentimes in chemistry, before you actually start your experiment, you have to make sure the solution you want to use is the correct concentration. So like, for example, when I prepare to teach labs, or at least when I did in the past, Carolina does it for me now. We talk about this all the time. I do actually have to do dilutions to make sure the solutions are the correct concentration before you get to lab. Basically, what we have in the stock room is a huge bottle of HCl, for example, and it's usually something that's extremely concentrated, like 12 molar. 12 molar HCl is extremely concentrated and extremely dangerous to work with. You should always be working with it in a fume hood, and I accidentally opened a bottle once, not in a fume hood, don't tell anybody, I felt it in my nose hairs. I felt it burn my nose the second that happened and immediately realized the mistake I had made. So when you have an extremely strong solution like that, that's not going to be the HCl that I give you guys to work with in lab. That's way too dangerous. I tend to give you something like 0.1 molar HCl. So we have to dilute them before you use them. So we go in the back room, we do all these calculations, we figure out how much we need at first to dilute to a specific amount. That's kind of the idea here, and we have an equation to do that. You may have actually heard me talk about in lab before that I was attempting to make a solution of HCl, and I happened to make it 10 times stronger than I meant to. And this is why. It's because I didn't actually write down my math and pay attention to what I was doing. I tried to do all the math in my head. I used the equation wrong, and I ended up with a solution that was 10 times stronger than I meant to. So that is a cautious tale of this is why A, dilution matters, and B, why you have to make sure that you write down your work and you are very careful about this, or you're going to end up with 10 times stronger acid than you meant to, which is no bueno, not good, Gucci. So, one thing I want to point out here before we actually work through some examples of how to use this equation, you see down here at the bottom. One quick note about that dilution equation you see down here at the bottom. It is the first molarity times the first volume equals the second molarity times the second volume. So again, we're talking about time periods here, so we're going to have to watch for initial and final, start, end. Oh, I want to start with this, dilute to this, kind of a deal. So please be wary that this is the equation we're going to use. We're going to have to watch those time periods again. And as another reminder, another thing I want to point out is you must use molarity for concentration and you must use liters for volume in this class. So we're going to do molarity times liters, and realistically we're doing that in the background because that molarity unit is moles per liter. So anytime we're using our volume in this equation, it makes it so much easier and it makes our life way better if we just use liters from the start. So you must be using molarity and liters. So if you see units that are in anything else, it should be a huge hint that maybe you got to do some conversions. So we're going to go ahead and work through the first example under calculating dilutions. This problem here says, what would the final volume of the solution be if you wanted to dilute a half liter of a 12 molar HCl solution to 6.00 molar? So this is kind of the situation I was talking about in lab. So the other day when I was working with my Chem 101 class, we actually used 6 molar HCl. So we were in the back room, we had to take that 12 molar solution, and we had to make sure in the end we ended up with 6 molar. So we worked with an equation just like this. So if I'm looking at my problem here, I'm going to write down what I'm given, I'm going to write down what I need, and I'm going to triple check the units first and foremost. So here it is given that we have Okay, what would the final volume be? So we're looking for final volume. So that means here, my first volume that I'm given, that 0.5 liters, is V1. So V1 is 0.5 liters. And because that 0.5 liters is attached to that 12 molar HCl, that 12 molar is going to be our M1, 12.00 molar. And then I'm saying dilute that to 6 molar, so that kind of dilution 2 tells me that 6 molar is going to be my time period 2, so that's going to be M2, is 6 molar. And then what I'm looking for, what I need, the question here says, what would the final volume be? So I want to know V2. So I'm going to go ahead and set up my equation. My units look like they're right. I've got liters, I've got molarity. Checks out. So in that case, I have M1 V1 equals M2 V2. So I have 12.00 molar times 0.5 liters. That's my M1, my V1. I have M2, which is 6.00 molar, and I'm going to multiply that by V2. So I've plugged into my equation. I can go ahead and begin the process of solving this. So to get V2 by itself, I'm going to go ahead and divide both sides by 6.00 molar, 6.00 molar. And then that leaves me with V2 by itself. And we're going to say that V2 equals 12.00 molar times 0.5 liters divided by 6.00 molar. If we go ahead and we take a moment to check out our units, we see that we've got molar on top, molar on bottom. Those are going to cancel out. We're left with liters, which makes sense. We're looking for a volume, so we would be looking for liters. So I'm going to go ahead and do the math here. And we'll see what we get. So I have 12 times 0.5, which is going to then therefore be divided by 6, which gives me the number 1. However, in this case, we also have to recognize the fact that we have to make sure our sig figs are okay. So if I go back to my problem and I determine how many sig figs I have, it looks like I have 4 sig figs, I have 3 sig figs, and I have 1 sig fig. So my 1 liter stands. I have my answer in the appropriate number of sig figs. I was looking for a volume, and I'm given liters. My answer checks out here. So go ahead and follow along. We're going to move on to the second problem that you see on your screen. So this problem says here, when working in a lab, you started with 256 milliliters of a 1 molar solution of vinegar. When you are done with your work, you now have a total volume of 487 milliliters. What is the new concentration of the solution? So let's go ahead, figure out what we're given, what we need, and we can solve. So, given. Here, we are given, looks like you started with this much at this concentration, so that's going to be V1 equals 256 milliliters. And my first concentration, therefore, is going to be 1.00 molar. If I continue on reading my problem, when you are done with your work, so it says when you are done, that's going to indicate to me my second time period, and I see a volume here. So my V2 is going to be 487 milliliters, okay? So we now need to figure out what we need as well. So our need, N-E-E-D, is what is the new concentration? So if we're talking about a concentration, we're talking about a molarity. So new molarity is going to be M2 equals question mark. So that being said, let's go ahead and check this out and decide if there's anything we need to convert. Ding, 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 ding. Red flag, ring the bell, something's wrong. I have milliliters, not liters, so I'm going to go ahead and need to convert these two values. So in this case, I have 256 milliliters, and I want to convert that to liters. There are 1,000 milliliters in 1 liter, so that's going to put 1,000 milliliters on the bottom, so my milliliters cancel out, 1 liter on top. That gives me 0.256 liters. And then I'm going to do the same for 487 milliliters, so that's going to be 487 milliliters times 1 liter divided by 1,000 milliliters. Same setup, we're doing the same thing. So we end up with 0.487. Oh, sorry, that's liters, not milliliters. So that's liters. So I can go ahead and write this over here into my chart so I can keep track. And, oops, I did it again. I called that a milliliter, didn't I? So, now I can kind of keep track of what's going on. I'm going to go ahead and erase my conversion work just so I have a bit more space to work with for you guys. So, that being said, our equation is M1V1 equals M2V2, and we can go ahead and plug in and solve. So in this case, we're given that M1 equals 1.00 molar, V1 is 0.256 liters, and then we are given that M2 is what we're looking for. We're actually not given that. Slip up in the words. And then V2 we are given as 0.487 liters. So from here, we need to go ahead, start working on solving, so we need to get M2 by itself. So we're going to divide both sides by 0.487 liters, divide both sides by 0.487 liters, and what that leaves me with is M2 equals parentheses 1.00 molar parentheses times 0.256 liters divided by that 0.487 liters. Well, I have M by itself. I'm going to go ahead and start to make sure I'm looking like I'm in a good place. Well, it looks like I've got liters on top, liters on bottom. I'm left with molarity. It's what I'm looking for. Checks out. So that means that M2 equals, equals 0.52566735511 molar. However, if I'm looking at my problem, I need to make sure I'm in the correct number of significant figures. So here I have 3 sig figs. These zeros count, so here I have 3 sig figs as well. And here I have 3 sig figs. So I'm going to go for 3 sig figs, so I'm going to write this as 0.526 molar. So that is how we go ahead and we solve to make sure that we know, we kind of know different concentrations and volumes and how to go between those different concentrations and volumes. So go ahead, make sure you work through the practice problems in the calculating dilution section as well. And I will meet you back here for part 2.